So hello, welcome to another day of Physics 2. Today we are going to sorry, I misspoke. Today we're going to start chapter 27. Well, apparently we're going to verify something on my computer. Come on, make that go away. Go away. This is going to be kind of interesting. So last chapter, chapter 26, we introduced, in general, just reflection and refraction and the effects of reflection and refraction. What we're going to do now is we're going to talk about how to use reflection and refraction. Basically, last one was the in theory how this stuff works. Now we're going to do the more practical use. Why are you verifying things? The more practical use. And we're going to talk about how just dealing with lenses and mirrors. Now, before I get into this, I do need to point out that chapter 2 is coming. This is the last chapter on exam 2. Well, chapter 2 is Friday, November 6th. This will be full problems again, just like they have been. So one problem, just one problem each chapter. So, one from 24, one from 25, one from 26, one from 27. At the end of this chapter, I'll give a little more detail and more exact. I have yet to start writing this exam, so we'll have to work out some. It will be the same. That is wrong. It says at noon, but this one will not be noon. Let me fix that. As you get to see my cat on the visualizer. This exam is not at noon because this one's going to be during the class that's left over from the physics class. This exam is going to be at 3 p.m. and you have to upload everything by 4:05, just like the last exam. I will be on Zoom if you have any questions, and I always recommend an equation sheet. I will be going through last year's exam. I didn't do it last semester, it's last year. The last year's exam is already up on Vanco Hall, so you can look at it and try to figure out what type of things I asked. I also will go over the solutions on Monday, a week from today, and we'll post that video and everything. And then Wednesday will be an extra day review, just like exam 1. Any questions there in general?
Nope.
I already had mentioned this, but in an email, but the final exam schedule was posted, so I now know when final exams are going to be. Your final exam is scheduled for Monday, December 14th from 5:30 to 7:30, which I think is a really fucking crappy time for an exam. I'd rather not have it doing when I would like to be eating dinner, but I have no sway over this. So that's when it is. I do plan on leaving it open till 7:45 to give extra time to upload if need be. More details about this exam will come as we approach it. I have yet to really put much thought into writing that exam yet. I will say with dealing with the final exam, I'm still probably going to have, like in Physics 1, where you have to do 8 out of 9 questions and 1 question won't be graded. But that's really hard to do in Vanco Hall. So I have been working on finding a workaround for that. So we'll see how that comes out. But just wanted to give that date because I knew it. Also, as one last little update, I have to move my office hours on Friday. I usually have office hours 10 to 11:30, but I have a meeting I need to go to from 10 to 11. So I am moving them to 9 to 10 and then 11 to 11:30. That's just going to be this week. Won't be always. Just had to move an office hour. Sound good? So what we're actually getting into the actual, physics and not just announcements, is, as I said, we've been talking about reflection and refraction. And we're going to talk about how to harness reflection and refraction. She just scared me. She jumped and the thing she was standing on went flying. We're going to talk about how to harness reflection and refraction in order to purposely go and direct light. I have in front of me a little lens, and if I put this lens between the camera and me, you can see I can start messing with the image of me where I look upside down. And depending on how I move this, maybe gotta get lined up right, where I look enlarged, like I have a much bigger eye, or maybe look much, much smaller, depending on how I move it. How we can take this and make it so, I can see, or else I wouldn't be able to. Now, mirrors in general, this is kind of one of those no shit Sherlock type things. Mirrors are based off having the light reflected. And a good mirror should be almost 100% reflection, 0% refraction. That's never really the case. There's normally some reflection, some refraction in any setup. But we're just going to assume a perfect mirror, that all the light's reflected, no real light is refracted in. Lenses will be the opposite, where it has all refracted and negligible amount of reflection. Once again, that isn't really the case. Like when I look in this lens at the screen, I can see the light ahead above me that's reflecting off of it. There usually some light will be reflected, but we're going to, for the most part, ignore that and talk about just the refraction in a lens. But the idea for both of them is just using it to direct light waves to an exact spot, a place where you want the light to be, and in a way to focus the light and, yeah, line it up. Okay? And we're going to start with the simplest thing we can talk about here, a flat mule. A flat mule is this idea at its simplest. And the general idea is when you look at an object really, if you look at an object in a mirror or lens, this would be true, but mirror especially, is what's going to happen is when you look at something off a mirror, when you look at anything, when you look at a thing, what's happening is light is shining on that object, it's bouncing off, and light from that object is going to your eyes. That's how we look. So when you look at an object in general, it's light coming from the object to your face. When you look at something in a mirror, its light is coming from that object, bouncing off the mirror, coming to your eyes. And what we can do is when you look at something from a mirror, and we're going to say an object at point O, we would talk about the distance from the object to the mirror. The distance from the object to the mirror, which would be the same for a lens, the distance from the object to a lens when we get there, will be referred to as P. Well, P is the object distance. I have no idea why it's P. Actually, I have a guess why it's P, but it's really just a guess. But P is the object distance, how far from the object to the mirror. And what happens when you look at something is light rays come from the object, they hit the mirror, and they bounce off the mirror, following the law of reflection. The angle of incidence equals angle of reflection. Now, really, your eye is not a point. It's small, but it's a range of height from like there to there for your eye, right? And so when light comes to something from your eye, there'll be some light that comes directly to the middle, but some that comes to the bottom of the eye, some that comes to the top of the eye. And we can say when you look at something, you can talk about a series of rays coming from the object, bouncing off the mirror, following the angle of the law of reflection, going towards your eye. The nice thing is well, not the nice thing. The weird thing is human brains, we understand what reflection is. We understand that, hey, I look at this mirror, the light bounces off. The thing isn't, this is not like through the looking glass. If I look at something in a mirror, I don't think there's something on the other side of the mirror or some crazy world. We understand if I see the mirror, it's probably behind me or, is just me. But physics-wise, our eyes can't tell the difference. That's just our brains being able to work things out. In fact, if you put like animals in front of mirrors, you'll find they'll often attack the mirror or just respond as if it's another one of that creature. Cats in front of mirrors can be fun. The reason why is because our eyes can't necessarily translate that the light is reflected. In fact, what happens is if you are looking at something in a mirror, and if the light rays are bouncing as drawn here, you could say this would be the same as an object that if you just follow the light rays from your eye and remove the mirror, would be the same as something in that spot. And what it is when you look at something in a flat mirror, we'll get other mirrors in a second, is you see as if there is an image. An image being, it's as if the thing is there. Well, and that image is just, that is what when you look at the mirror, it seems like there's something else behind the mirror. That is the image. You see if you're looking at you in a mirror, you see another you that far behind the mirror. And we'll say that it looks like there's another you behind the mirror, a distance q away, where q is the image distance. I said I had a guess why they use P and Q. I think it's literally because P and Q all look reflected in a mirror, but I don't know. And what it is when you look at the mirror, P is the real distance, the distance between the object and the mirror. And a Q is where it looks like the image is. The distance, how far away from the mirror it seems to you. There isn't something at I. It's just how far away from the mirror it looks. This is going to get into if we don't have flat mirrors. I'm getting ahead of myself. We're going to not do flat mirrors, but the whole like object and mirrors are closer than they appear type thing. That's because that it doesn't always seem like it's the same distance for P and Q, but it's where it appears to be. Now, for a flat mirror, P and Q will be the same. When something's in front of the mirror, it'll look just as far away on the other side. Also, with a mirror, it's what forms what is called a virtual image. So if I shine light through this lens, I can take it and focus that light to a point. Or I could focus an image. That I can shine an image through this, like a projector, right? That if a projector focuses an image on the wall. Anytime you can focus an image to a point, that is called a real image. It's an image where you can focus the image onto a screen. A virtual image cannot be focused onto a screen. And what it is that the light rays don't really line up anywhere, only theoretically if we assume. In this case, the light rays from the actual object to the eye, they only line up on the object. They don't line up anywhere else. Really, we can pretend it's kind of like they line up at eye, but they don't really. And that is a virtual image. A virtual image cannot be focused on a screen. For a mirror, when you look at mirrors, you normally look at things reflected on the same side of a mirror. Any image that exists on the same side of the mirror as you will be a real image. And any image that appears on the opposite side of the mirror of you will be a virtual image. Now, how you can have the image be on the same side of the mirror of you, we will get to in a little bit. But for a flat mirror, that's not going to happen. It'll always be a virtual image. Now, if you want to know where it looks like the image is, that if you have an object at point, at some point, where does it appear the image is? What we're going to do is you have to draw at least 2 rays of light from the object. And most of the time when we talk about what something looks like reflected in a mirror or a lens, we're going to talk about things, we're going to talk about, looking at an object in a mirror lens, we're just going to treat it as an arrow. And we're going to say our object is this gray arrow here. That's a distance P away from the mirror. And we'll just say that's our object, an arrow pointing up. How big the arrow is doesn't really matter. And we can say, we'll say light for this from this object. We'll talk about 2 things. One that goes straight across and bounces straight back, and then one that goes down to the middle of the mirror. And the one that goes down to the middle of the mirror following the law of reflection. Now, the one that goes straight off and straight back, it's coming in at 0 degrees, so it's going to come back at 0 degrees. That's going to be just, there and back and nothing special. The one that goes down to the middle, I'm going to say this angle here, theta, equals that angle there, theta, following the law of reflection. But the general idea is if I want to find out what this image looks like in the mirror, I will follow both of these lines back. That I'll say this ray right here, let's follow it further backwards. This ray right here, let's follow it further backwards. And there will be a spot where they overlap. The spot where they overlap, that will be your image. And that's what it looks like you see in the mirror. Now, normally we can talk about the height of the object. The height of the object is traditionally written as h. The height of the image will be written as h prime. But for a flat mirror, for any flat mirror, P will equal Q. And also, if I want to compare the height of the object, h and h prime, for a flat mirror, h will equal h prime. Now, for any flat mirror, you will see a virtual image, because on the opposite side of the mirror, the same distance away from the mirror as it was in front of it, and at the same height. It will look like it will look exactly the same height. Okay. Now we can also talk about magnification. Magnification is not going to come into too much play here for a flat mirror, but I want to introduce it now. Magnification is a way of talking how much the size of an image looks. That it's just how much the size of an image changes, where it's just the height of the image divided by the height of the object really is. Which means, ooh, I have a slight mistake here. There's a very slight mistake on this next bit, and I will just fix it by drawing all over it. Which means it's, let me make sure I don't, hold on, I want to check something. But that just means it's going to be h prime over h. Yep, it should be h prime over h. I wrote that backwards though. And so since h prime and h is the same, that means it has no magnification. This is a magnification of 1. Magnification, which uses the symbol capital M, is a unitless quantity and just is what ratio the size changed. For all flat mirrors, there will be a magnification of 1. And yeah, h prime over h, not the other way. I will fix that on the slides. Okay. So in summary, flat mirror. The image is as far behind the mirror as the object is in front of it. The image is unmagnified because m equals 1. And often for mirrors, we'll talk if something's magnified or reduced, if it looks bigger or looks smaller. But for a flat mirror, it's unmagnified. It looks the same size as it originally was. It'll be virtual because you cannot focus it on a screen. And I haven't talked about this one, but it's also upright. That if you look at something pointing up, it's still pointing up. Once again, if you look through the camera and you look at me through this lens, I'm upside down. That is called inverted. That sometimes an image will be flopped up and down. But that's not true for a flat mirror. And so we can say for any flat mirror, we have an unmagnified virtual upright image. Now that being said, a flat mirror does have a left-right reversal, right? That if I lift my left hand, it's actually, no, Zoom flips it. It should actually be on your left because Zoom flips. What I see is different from what you guys see. But in general, you look at something in the mirror, if you, like any writing would normally be backwards. That an image just a left-right reversal. The reason a flat mirror does a left-right reversal, you actually can see if you draw out the images of something. Let's say I'm going to look at this arrow on a flat mirror, right? I can say the light rays from the front of the arrow will bounce, follow the law of reflection, and go to my eye. The light rays from the back of the arrow will bounce, follow the law of reflection, and go to my eye. Well, if I follow these light rays further, this right here is the one for the tail. So I'll follow, well, you know what, let's do. This was the light ray that went to the tail, so I'll follow that up. This light ray was the one for the pointy part of the arrow, so I'll follow that up. And what you find is that the tail versus pointy bit are in the opposite direction, that it flips it around. And that's why, it's just following the light rays. Now, flat mirrors are simple and really, like, I probably already spent more time on them than is really justified. Where this gets interesting is when your mirror is not flat. And we're going to talk about 2 different types of curved mirrors. And the 2 different types of curved mirrors we're going to talk about are concave mirrors and convex mirrors. Concave mirrors, which, if you can't remember which one's which, concave mirrors are one if a curve, anything that's a curve, you can say is part of a sphere, right? That if I have some nice round thing, if I have just a piece around it, I can just say it's some small piece of that round object. A concave mirror or a converging mirror is one with the shiny part is the inside of the sphere. And the best way to remember it is it's like a cave. You're going into the inside. A convex mirror is one where you're on the shiny bit is the outside of the sphere. And I have something to display here, but I'm going to do it now. Now, a concave mirror is also known as a converging mirror. And the reason why is if you have parallel light, like I show here, and you shine this parallel light on a concave mule or a converging mule, it'll focus all the reflected light to one point. That point called the focal point. Well, here the focal point, you can kind of tell what it is. All the light is focused right there. That is why it's a converging mule. For a diverging mule, also known as a convex mule, when a light bounces off the outside or the convex mule, all of the light will be also focused to some point. What's that? That's a lie. All that will be focused away from some point. It'll all spread out. It will diverge, hence the diverging mule. If you were to take all these diverging light rays and just say, where would they be coming from? I can't tell where that one is, so I'm going to do this one. That if I follow them through, where would they be coming from? You'll find that they all diverge from some point, which I think my last one is what, like here? That point they all come from, in this spot in this case, that is also a focal point. And that's just where they come from. And so so for parallel light, a concave or converging mirror focuses the light to the focal point. A diverging mirror or concave mirror focuses all the light away from that focal point. But as I said, we're going to treat these mirrors as if they're part. What changed though? Okay, we're going to treat these mirrors as if they are part of a sphere. And let's just start with concave. For a concave mirror, if this is just a part of a sphere, I could say any sphere will have a radius, all right? I'm saying radius, capital O. I'm going to define a point C as the center of curvature. That if this was a sphere, C is the direct center. We're also going to define a point V. V that I'm literally forgetting what V stands for right now, and I didn't write it here. Like the actual, it has a word that it's short for, but I forget what. But V is the center of the mirror, wherever the direct center of the mirror is. In a second, I'm going to do more with seeing these mirrors. But if this was my mirror, C would be a point on the mirror in its direct center. Not the center of curvature, but the center of the, oh, you're not doing what I'm telling you to do. But the center on the actual mirror. If you draw a line connecting those 2 points, that is called the principal axis. And the principal axis is what we're going to base everything off. It just goes from the center of the mirror through C. Now, if you put a object on the principal axis, what's happening, and it has this light spreading out, all of the light will go and spread out, and all the light that hits the mirror will bounce off the mirror following the law of reflection. And what happens is, because it's a curved mirror, right? Like here, the normal of the mirror is flat, but here the normal of the mirror is there. Normal of the mirror is going to be like this. That as the mirror goes around, the normal is going to be at different angles. And if you put something on the principal axis, that if you look at all the reflections it can make, all of the reflections will converge on one set spot. That they will go out, bounce off the mirror, come down, and all converge at that same spot. Now, because all of these light lines converge on a spot, because they all line up, this would be a real image, which can be focused on a screen. And even though there's not going to be anything physically there, that if you look at something in a curved mirror, you'll see a image that, you can see something in the mirror, but it's a real image, because if you have a screen, you can focus it. And we will focus light and make real images with concave mirrors in one of the labs upcoming. Okay. Now I am making an assumption here. My assumption is that this is a small angle with the principal axis. If you do a big enough angle, things do not line up correctly. If you have a very big curved mirror, that's not big as in it covers a large angle, you usually get a blurred image. but for small angles, this can work. Okay? And what we can say is we can figure out exactly what an image will look like in a concave mule, as long as it's a small angle. And we're just gonna geometry the shit out of this to work out how it works. Let's say I want to look at an object in the mule, and I'm going to say my object. Once again, I'm just going to draw my object as an arrow of height h, and that object is a distance p away from the mule. I'm going to draw two rays coming off my object. I'm going to do one ray. I'm going to have go straight down and hit through C. If this goes straight down and goes through C, it's actually, if it goes down through C, it'll hit the mule at 0 degrees, which means it'll reflect directly back by definition. The other line is going to go through V, and it's going to follow the law of angle of incidence, or law of reflection. So the angle above theta will equal the angle below theta. Wherever these two lines meet, that will be where my image is. I'm going to define that as I right now for this moment. And I can say where those meet, that will form the image. This is on the same side of the mule as the object, so it's a real image. And I'm going to say wherever they meet, I can draw a new arrow to represent my image. And this image will consist of an arrow. I thought I wrote it there. I don't write it anywhere. I'll just mark it out. This image will consist of an arrow coming from the principal axes to wherever they meet. So in this case, it's an upside down arrow right there. From the principal axis to the meeting point. That is what the image is going to look like. Now, if you look at this setup, this arrow is pointing down when the object was pointing up. If your image is pointing down while your object was pointing up, that is an inverted image. Also, H and H prime aren't the same. That H prime is noticeably smaller than H. That means this is going to be a reduced image. It's going to look smaller than it really was. Now, there's a bunch of equations to simplify all this. But to get to the equations, we're going to have to do some crazy geometry. And so I'm going to talk about a few different triangles. My first one is going to be this triangle right here. And I'm going to say the tangent of that angle, SOHCAHTOA, tangent, opposite over adjacent. So the tangent of that angle is h over p. But that's the same as this triangle right here. And the same idea, SOHCAHTOA, the tangent of that angle is negative h over q. I'm saying negative h prime over q. I'm saying it's negative because it's down. And q is, we already said, q is the image distance. We covered that for the flat mule. But the law of reflection says both these angles are the same. And if both of these angles are the same, the tangent of both of these angles is the same. So h over p must equal negative h prime over q. Rearranging, that tells me that h prime over h equals negative q over p. And therefore, we can say the magnification of anything in a curved mule will not only be given as h prime over h, but can also be found with negative q over p. Now, I said before, I mentioned it quickly, but only for a second. Anytime you get a negative magnification, negative magnification doesn't mean bigger or smaller. Magnification bigger than 1, it's bigger. Magnification less than 1, it's smaller. What a negative magnification means is inverted. If you ever get a negative magnification, the image will be upside down. Okay? Now, this is going to be one of our first equations for mules, that the magnification is always equal to negative q over p. It's equal to the image distance divided by the object distance. If we also look at alpha, this little angle down here and down there, I can say the tangent of alpha is opposite is opposite over adjacent. That's h over p minus o, where p is the image, p is the object distance, and o is just where c was. But if I look at this other version of tangent, there I get that tangent is negative h, once again because it's down, o minus q, because o is going to be from here to here, and q is from here to there. So that little distance is just o minus q. But once again, alpha equals alpha, so I can say that those two things must be equal. Rearranging, I can get this equation. There was a very small math error here that I'm going to have to fix. Oh, no, there isn't. I found it. I thought I had a math error, but I literally just didn't see this negative sign. But if h prime over h is negative o minus q p minus o, we know that h prime over h is negative qp, or q over p. So I can set those equal. And then just a pause for algebra. So for some quick algebra, we're going to take that, slide that up to the side. If that is true, I can cross multiply it. When I cross multiply, well, I didn't cross multiply. I just multiply both sides by p minus all. If I multiply both sides by p minus all, that stuff cancels out. When I do that, that gives me this mess. So I'm just going to take this and I'm going to multiply both sides by p. When I multiply both sides by p, these p's cancel out, giving me that. Basically, I didn't cross multiply. Then I will factor through. When I factor through, that equation becomes this. Once I get that, I can say, hey, look, there's a PQ on both sides. I'm going to add PQ to both sides, and I'm going to add this to both sides. I'm going to add that to both sides. Basically, I'm going to take anything negative and add it to both sides. That gives me this guy. Then I'll go and I'll say, just for fun, let's divide both sides by all PQ. There's a reason I'm doing that, or it'll make sense in a second. If I divide both sides by all PQ, I can cancel out some O's, I can cancel out some PQs, and I can get this guy. That's a kind of weird thing to do, but if I take this, I can factor this out, and I can say P plus Q over PQ is the same as P over PQ plus Q over PQ. Each of those pieces of the fraction can be reduced, and that'll give me this. I did that fast on purpose. You'll never need to do that algebra, but I'm just showing that it's logical. And I get this equation, that 1 over p plus 1 over q equals 2 over o. This is called the mirror equation. And for any mirror, you can find exactly where the image will be. That if you look at a curved mirror, you know how far away the object is from the mirror, you can tell how far away the image will be from the mirror, because you just say that 1 over the object distance plus 1 over the image distance is 2 over the radius of curvature. Now, if you have something very far away from the mirror, so it's like infinitely far away, which is what's going to happen if you have parallel light, like I had in my videos here with this parallel light. If I have parallel light, P will be about infinity, which means 1 over P will be 0, which will mean 1 over Q will be 2 over O, or Q will be O over 2. That means all of the light will be focused at half the radius. Now, when I showed this video, I said the place the light is focused is called the focal point. I had used that phrase. And that is true. All parallel light hitting a concave mirror will focus at the focal point. And what we just found is that the focal point for any curved mirror will be half the radius, halfway between C and the mirror. And that makes our equation in the upper right reduce to this, that for any concave mirror, 1 over P plus 1 over Q equals 1 over F. And that'll be true for any concave mirror. The equations you need to know here, I went through a lot, and I'm going to simplify this in a second, is this this, and this. Everything else was derivations. Okay? Any questions?
No.
Okay, let's say we're looking at a convex mirror then. I can do the same thing with a convex mirror, a light that goes straight from the top of the object through C. But when light goes straight to the top of the object through C, now C is gonna be on the inside of the mirror. That C is not gonna be in the part the rays ever get to, because it's always the center of curvature. And in a convex mirror, you're looking at the outside of the sphere. And I could do all of the math I just did. And guess what? I'm not gonna do all of the math I just did, but I could. And if I did all of the math I just did, I would get all of the same equations with one minor difference. I would still get that the magnification is h prime over h, or negative q over p. I would still get that 1 over p plus 1 over q equals 1 over f. What would be different, and the only thing that is different, is this negative sign. The focal length of a concave mirror is all over 2. The focal length of a convex mirror is negative all over 2. The reason why is because the focal point is on the opposite side of the mirror as an image. For a mirror, we would define things on the same side of the mirror as the object as the positive, and things on the opposite side of the mirror as the object as the negative. And because the focal point is the opposite side of the mirror, it will be negative. And we can actually, if you derive using the same algebra we just did, you would get that comes out in the equations. Okay? In fact, to go further on this idea, for mirrors in general, we need to pay attention to the signs. And I'm gonna jump ahead for a second. We're gonna talk about lenses also. When we talk about lenses, every convention I'm about to say here will not be the same. Mirrors and lenses have different sign conventions. So be careful. You're gonna wanna keep a section for lenses, a section for mirrors. But for mirrors, we are gonna refer to everything if it's in front or in back of the mirror. In front of the mirror means that it's going to be on the reflected side. In front of the mirror does not mean left, right. It just means it's on the shiny side. In back of the mirror is on the side that isn't shiny. Now, almost always your object distance will be in front of the mirror. If you're looking at an object in the mirror and you put it behind the mirror is not going to work very well. If P is positive, that means it's in front of the mirror. It should always be positive. Q will sometimes be positive. Q will sometimes be negative. If Q is positive, it is a real image and exists on the same side of the mirror as the object. If Q is negative, it is a virtual image and will be, you can't focus it on a screen, but it just means on the opposite side of the mirror as the object. Likewise, focal length. Your focal length is positive if the focal length is on the same side of the mirror as the shiny side. And what that means, if you have a convex mirror, F is negative. If you have a concave mirror, F is positive. I did that in opposite order and I just confused myself for a second. Then if the focal length is in front of the mirror, that is concave or converging. That is positive. If your focal length is behind the mirror, that means it is a diverging mirror or concave. Or it's negative or convex. For magnification, if magnification is positive or negative, that has nothing to do with size. It's just positive magnification. Positive magnification means it's upright. Negative magnification means it's inverted. However, the magnitude of magnification. If magnification is greater than 1, it's magnified. If magnification is less than 1, it's inverted. In general, I'm going to ask things like, is it magnified or reduced? Look at the magnification. Is it bigger than 1, less than 1? Is it upright or inverted? Is your magnification positive or negative? Is the image real or virtual? Real image, Q is positive. Virtual image, Q is negative. And keep in mind, for a mule, P will never be negative. P will never be negative because if you do, you're on the not shiny side of the mule. Now, this can lead to whole sorts of stuff. Let me go to my video before I go through. This right here is a concave mule, and I'm pretty far away from it. When I'm pretty far away, I am reduced. I look smaller. I am upside down, meaning I'm inverted. And when I move closer, I'm going to start getting bigger and bigger, and eventually, I'm going to flip to right side up. When I flip to right side up, it's not that I changed anything. I just got closer. I went from inverted to not inverted. And I also got magnified. I got bigger. When I move further away, I become reduced and upside down again. For a oops, get one of that. No. For a concave mule, if Q is for a concave mule, Q will be positive because Q will always be positive, and F will be positive because that's what a concave mule means. If you all, depending on your distance away, you might get a positive Q. If you are far away from the object, Q will be positive. If Q is positive, that means the image is real. But if Q is positive and P is positive, M must be negative. And therefore, anytime you have a real image, it will be inverted. And this will happen anytime P is much bigger than F. Like when I was way out here. If you get closer to the mirror, your Q can become negative. If your Q is negative, it is a virtual image. And when your Q is negative, it doesn't mean there's no image. This right here is a negative Q. You still see me. You just can't focus it on a screen. And when Q is negative, because M is negative P over Q, if Q is negative, M must be positive. And therefore, anytime Q is negative, it must not be inverted. But it's not a real image. And so for a concave mirror, you can have a real image, you can have a virtual image. You can have magnified, you can have reduced. You can have upright, you can have inverted. However, for a convex mirror, I am always upright. And on a convex mirror, it is always upright, and I kind of look a bit smaller than I normally do. For a convex mirror, F is negative. And because F is negative, well, think about it this way. If I have something plus something and I get a negative number, one of these two must be negative. P is never negative. And so if F is negative, because it is by definition by a convex mirror, Q will always be negative. For a convex mirror, M will always be positive, it'll always be upright, and you will always have a virtual image. And just for fun, for a flat mirror, R is infinite. Because R is infinite, F is infinite. If F is infinite, that means 1 over P plus 1 over Q equals 0. And so you always get the P equals negative Q. P equals negative Q means you have an upright image, it isn't magnified, and a virtual image. So, if I tell you the curvature for a mirror, and if it's convex or concave, you can use this to figure out exactly how far away the object is from the mirror, but also what it looks like. Is it magnified or reduced? Is it upright? Is it upright or inverted? Is it magnified? Is it virtual or real? We good so far? That is only one way to find that information, though. These three equations are the mathematical way. And honestly, that's the way you're normally going to do it, the mathematical way. But you can also work out all this stuff by using what is called a ray diagram. That if you don't want to do this math, let's be honest. For us, That's pretty simple math. But if you don't want to do the math, you do a ray diagram, which is a way of drawing this. Basically how I first derived it. And what you do is you draw your meal and you measure you draw the meal, you draw your principal axes, and you mark the center of curvature. And you mark your focal point, which is always halfway to the center of curvature. And you draw your object as an arrow from the principal axis. And from that, you would draw two lines. One that goes straight across, parallel to the principal axis, through F, and one that goes from the top of your object through C. Wherever these lines meet, that will be your image. And you can actually figure out all those things, the magnification, P, Q, if you just sit there with a ruler and measure and figure it out. I think this makes no sense just written on a screen, so let me show you what I mean. Let's say we had this setup. We have an object that is about, I'm just putting my ruler literally on the screen, so it's useless. But I have an object about 19 centimeters away, and I have a center of curvature about 8 centimeters. That means my focal point's at 4 centimeters. And if I want to draw this, I'll draw two lines. My object just being an arrow. I draw a line straight across, then through F, and I draw a line from the top of the object through C. Wherever they meet, that's where my image is. And I can say my value of P is the distance from the mirror to the object. My value of Q is my mirror to that arrow I drew. That arrow is on the same side as the object, it's real. That arrow is smaller, it's reduced. That arrow is pointing down, it's inverted. And if I measure the distance from the mirror to the image, I can get Q. And this is a convex mirror far away, a small inverted image. That is what we saw on those images, a small inverted image. If I have one that's closer, I do the same thing. Straight across through F. From the thing through C. Now, if I look at these lines, they're moving apart. They're never going to meet. If I extend this line and extend this line, they are literally getting further away. If you have lines that do not meet, just continue them in the other direction. Wherever they meet, that's your image. This is a virtual image because on the opposite side of the mirror. It is magnified because it is bigger. It is upright because it points up. This gives me the exact same information as long as I have a ruler and draw it very exactly as the math does. I can work out the magnification by measuring the height of the image, by measuring the height of the object, dividing them. I can get all that information with a ruler instead. Obviously, I'm normally going to have you do the math. Let's be honest. This is me. I'm going to do math and not arts and crafts time with a ruler. But I will say, if you have a convex mirror, same thing. You want to know where the image is? Line straight across through F, a line through C. Wherever they meet, that's your image. Okay? All right, I got 2 minutes left. I'm going to do one more point, and I'm going to start next class with an example problem. You know how the rear view mirror in a car says objects in mirror are closer than they appear? Actually, it's only one of them. It's the passenger side one says that, which is weird because that looks like the other side. But anyways, the reason it says that is we as a human understand that if you see something and it's smaller than it should be, it's far away, right? That like, yeah, if you see someone who looks really small, you don't necessarily think, oh, they're really small. They're just far away from you. And so if you see a small car in a mirror, it's far away. The mirrors on the passenger side on a car are convex mirrors. They're convex mirrors because when you make the mirror convex, it gives you a larger frame of area you can see. That instead of just seeing what's across, you can see stuff at the edges. But convex mirrors give a reduced image. Because it gives a reduced image, the image is smaller. That's why it says this. Things are smaller than they should be because it's a curved mirror to try to give you more vision. Any questions?
Nope.
Okay, we'll stop there. I'll pick up next class with an example problem, and then we'll do all this for lenses. Which I'm not going to lie, I'm not going to do much derivation for the lenses because we kind of did it already. They have very similar equations. But other than that, have a good day.